Hi, you probably learned about derivatives from first principles in school today and you were a little confused. Don't worry, I'm here to help. In this video, I'm going to be explaining what derivatives from first principles has to deal with. It's also known as the limit definition of a derivative. And I'm going to be explaining this before I move on to the different rules of differentiation because this is crucial to understand before moving on. Partly because the IB Math AAHL course tends to ask you a couple questions explicitly stating find the derivative of this function through first principles. So you're going to have to know that or you're going to miss really easy points. Otherwise, it's really also crucial to understand where derivatives actually come from, how it's actually derived in the first place, how people got to find the instantaneous rate of change or the derivative of a function or the gradient of the tangent at a specific point in the function. All of that was explained in the last video. If you haven't checked that out, go check it out. Another thing that you need to know before tackling this video is the concept of limits. So if you're not comfortable with limits yet, watch a couple videos about limits and come back to this video. So let's just say that we have a function with a graph that's shaped like this. And in the last video, I covered the difference between average rates of change and instantaneous rates of change. And I said that the average rate of change is basically the rise over run or the change in y over the change in x between 2 points on the function. So it could be these two, or it could be, these two, it could be any two, or it could be these two. The average rate of change is basically the change in y over the change in x between 2 points, right? And instantaneous rates of change differ from average rates of change because it's the precise rate of change at an exact point on the graph. Okay, so let's start off by finding the average rate of change of this function between these 2 points. And for, for a technicality, I guess, we'll label this point A, okay? And if we want to find the average rate of change, we need to know the rise over run, right? It's basically finding the gradient of the straight line that joins these 2 points. And we know how to find the gradient of a line. It's rise over run or change in y over change in x, which is basically this over this, right? For this case, let's just label the distance between these 2 points on the x-axis as h. And that way, we can give the second point the label of a plus h, right? What we can find from here is that the change in y is going... So this point on the y-axis, or, the y component, is going to be equal to whatever the function is when you put in a, so f of a. And conversely, on this height is going to be... the value is going to equal to f of a plus h because the coordinate is a plus h. You have moved h amount of times. So from this, we can derive the gradient of the straight line or the average rate of change between these 2 points. And let's just write that. So rise is going to be the change in height, right? Or the change in the y value. So it's going to be f of a plus h minus f of a over the run, which we already defined as h. So this is going to be the general formula for the average rate of change of any 2 points in any given function. Pretty clear, but what if we want to find the instantaneous rate of change, or precisely the gradient of the tangent line at exactly point A? So let's think about this for a second and start moving the second point closer and closer and closer to point A, all the way until h is technically 0, so that the 2 points actually become identical. And so, okay, let's try that. Let's make it so that h is equal to 0, and that way we'll be able to find the average rate of change between 2 points that are technically identical and in a way that'll make sense. But no, when we try and plug in h into this formula, we get a 0 in the denominator. And from middle school math, from elementary math, we know that you can't have a 0 in the fraction. Okay, So we can't do that, which is why we need the help of limits. Okay, so if you understand what limits are, we can basically define this as if we want to find the gradient of the line that meets only at point A, which is basically the instantaneous rate of change, we're going to have to write it as limit. We're going to have to write it as limit as h approaches 0. It's not going to get to 0. It can't, but it will approach 0. That's kind of the idea of limits. And we'll put in the exact same formula or the identity that we defined here. And so what this is basically saying is that h will approach 0, and it'll get as close as it possibly can to 0. And the limit of this function as it approaches to 0, as h approaches to 0, is going to end up giving us the instantaneous rate of change. So from this, we can conclude that the derivative, or f prime x, remember this is a notation, is equal to, and there you have it. That is a limit definition, and that is the derivatives from first principles. That's the idea behind it. One point moving as close as possible to another point, to the point where the line is no longer between 2 points, but it's just touching the graph at exactly 1 point. Okay, so here's a simple example to kind of put everything to perspective. It says, consider the function f of x equals to x to the power of 4, and use first principles to find the gradient function, which is the derivative of fx. Okay, so f of x, we know it equals to x to the power of 4, and we want to find the derivative of fx, which is written like this, f prime, which is also known as a gradient function. If we want to do that, we have to use the identity that we defined in the previous slide. The limit as h approaches to 0 of f a plus h minus f a over h. This is the exact identity that we defined, right? But in this case, we can sub a as x, right? Because that's what we're working with. We're not working with a, we're working with x. So if we do that, we need to find the limit of h as h approaches 0, f x plus h minus f x over h. So let's sub the values. Let's sub in the values. Make sure you write the limit until the last part. If we do x plus h here, we get x plus h to the power of 4 minus x to the power of 4 over h. Now, we just need to simplify and get. And if we expand it, we can do this, because x minus x is the same thing. It just cancels out. So then in the next line, we can take out the h and then eventually cross these out, and then we'll get the limit as h approaches 0 of 4x cubed plus 6x squared h plus 4xh squared plus h cubed. And if you know how to solve this limit, you would know that if we sub 0 into h, 0, 0, 0, the final answer becomes 4x cubed. If you've already learned the rules of differentiation, this might feel really stupid, but there's going to be questions that ask this explicitly. So be sure to know the process behind this. Part B just says find f prime of -1. So -1, and interpret your answer. So if we just do that really quick, it's basically just saying plug in -1 into this function that you already found. Right? Let's just do that. And then you'll get, -4. And it says interpret it. It basically just means the gradient of the tangent line at this point. So it's the instantaneous rate of change at exactly this point. So it's the gradient of this point on this function. So that's basically what first principles has to deal with. It's also called limit definition. Remember that. And this is just a thing that you kind of have to visualize. I don't think you need to really try and memorize this function. You can kind of just picture it in your head and be like, okay, so it's limit of as h approaches 0, blah, 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 blah. I think more than memorizing this, I think it's really important to just understand how things work. And the way I explained it, hopefully it was simple enough to the point where you can just kind of remember and picture, okay, so we go from the average rate of change to the instantaneous rate of change by bringing one point closer to the other point, to the point where they're basically identical. And we use the limit function because h cannot be 0 in the denominator. Blah, blah, blah. Whichever way you want to memorize, you can memorize the expression, or you can memorize the way it's derived. I would prefer to memorize the way it's derived because it just enhances your understanding. But that's all you need to know, basically. And once you understand this, you're ready to move on to the rules of differential calculus. So I hope that helped. I'll see you in the next video.